Okay, now we're going to talk about open pipe resonance, and here's the pipe that I use for closed pipes, and let me zoom all the way out here so people can see it. It's a pipe that's 50 centimeters long. Okay, it's just a PVC pipe. Okay, but what I'm going to do is this. I want you to listen to the fundamental frequency for when it's closed, and then I want you to think about the fundamental frequency when it's open. I'm going to open it up. So listen very carefully. Okay, now I'm going to open it. Closed. Open. Do you hear that it's the same note? But it's up an octave. It's one octave higher. Closed, open. Now, open pipe resonance, when you're just blowing across the pipe, it doesn't sound as sharp. It's not quite as good. But what I'm going to do is show you why it resonates at a higher frequency. If you have a fixed length of pipe, why does it resonate if it's open on both ends at a higher frequency? Well, here's what happens, and it's a little bit weird. I don't really understand exactly why this happens. I just know that it does. It has to do with boundaries and so on. Here's my pipe, but now there's no water down here, right? It's just open on both ends. So let's suppose I had a tuning fork, and I want you to pay attention. I don't want you to text on your phone or anything else. I want you paying attention up here. So the tuning fork is down like this, and it's creating a compression of air. And this compression, not the air molecules themselves, but the compression is going to move down the pipe at the speed of sound. So let's look at it right here. Something very weird happens. This compression travels down the pipe, and then it comes out this other end. It travels out. But the end of the pipe here acts like a boundary. And it acts like a loose boundary, an open boundary. And so what happens is that some of the wave, not all of it, not even most of it, but part of it, some of it gets reflected back up the pipe. But what gets reflected back is a rarefaction. I said fraction. Rarefaction. In other words, if this is a compression, what gets reflected back is a little bit of air that's stretched out, and it's going to move up the pipe. So most of it gets out the bottom, but some of it gets reflected up back like this. Now, let's go back and look at this tuning fork right here. The tuning fork creates a rarefaction on this side, and this rarefaction goes out into the world. I draw little circles to indicate a lack of air. Okay, here there's too much air. There's high pressure air. This is low pressure air. And the low pressure, when it hits your ear, when a rarefaction hits your ear, it kind of serves to pull your eardrum out of your head. The compression pushes it in. Now it doesn't really pull. What happens is that the high pressure side of your eardrum makes it bulge out and so on. But I don't want to get into that right now. And so what happens if this is length L? So what happens is that when this rarefaction is this is the reflected rarefaction, comes out and into the world for us to hear. Now let me ask you, just look at this. What do we want the tuning fork to be doing right here to amplify this wave? If a rarefaction is coming out of the pipe, we want the tuning fork to be making a rarefaction that's going to go out into the world, don't we? We want it to reinforce what it was doing. I mean, we want the wave that it makes going out into the world to match the reflected wave. And if they are exactly matched, they will constructively interfere. and you will get resonance. It will have a greater amplitude. So what happens is this. The tuning fork will be bent downwards. Now, yeah, it's making another compression right here, but this reflected rarefaction is piling on top of this and thus amplifying the sound. So what we want is something a little different. We want the tuning fork, if we're going to use a tuning fork to do this, we want it to go up and back down. So now, in a closed pipe, what did we want the tuning fork to do? We wanted the tuning fork to just go up. But now we want the tuning fork to go up and back down, which means the tuning fork has to be twice as fast. Which means it's going to be moving with twice the frequency. Which means the sound that resonates with the same length of open pipe as closed pipe, it's going to resonate at twice the frequency. Here's closed pipe, open pipe. Okay, so it wants to it will resonate at a frequency that's twice as high as it was when it was closed. And now let's take a look at this in terms of the length of the pipe. The sound goes down the pipe and up the pipe, doesn't it? So that's twice the length of the pipe is the total distance the sound travels. Down the pipe and then back up the pipe. But that's going to be equal to how much of a wavelength? How much time does the tuning fork have? It has enough time to go through a complete cycle. So therefore, twice the length of the pipe is going to be equal to 1 wavelength. Which means the length of the pipe is going to be half the wavelength of the sound. Now, we can extend the length of the pipe. Let's say we want to give the pipe enough length so that the tuning fork can do this. Up, down, up, down. So it's still going twice the length of the pipe, but now we're increasing the frequency, right? So it goes up, down, up, down. And so, well, actually, I can make the pipe longer. Let's hold the frequency constant and make the pipe longer. So this will be L1. So L1 equals the wavelength. Now, if I make the pipe longer, that will give the sound enough room to move so that it takes enough time for the tuning fork to go up, down, up, down. Which means twice the length has to be equal to 2 wavelengths of sound, right? Because up, down, that's 1 wavelength. Up, down is another wavelength. So therefore, L2 is going to be equal to the wavelength. But now I'm going to cheat a little bit. I'm going to say this is 2 over 2, right? It's the same thing, right? I'm just going to divide both sides by 2, and I get 2 over 2. Now, normally we cancel that 2 out. But what is lambda over 2? It's L1. So this is equal to 2 L1. Now, what if I made the pipe even longer? So now the tuning fork has time to go up, down, up, down, up, down. Well, twice the length of the pipe is going to be equal to up, down, up, down, up, down. How many wavelengths? 3. So L3 is going to be equal to 3 lambda over 2, which is equal to, oh, look at that, 3 L1. And then up, down, up, down, up, down, up, down, 4 L1. Up, down, up, down, up, down, up, down, 5 L1. Okay? So instead of the odd numbers, with closed pipes, only the odd number multiples of the fundamental wavelength would resonate. Now, I said that a little bit wrong, but now it's every integer. So we can say this. The length of pipe that will resonate, L sub n, will be equal to just n times the wavelength over 2. where n equals 1, 2, 3, 4. So this is the equation that gives us the different lengths of an open pipe that will resonate. Now I'm running out of time, so I'm just going to very quickly change this a little bit. Last thing, I swear. So we know velocity equals, if I'm off screen, tell me, because I can't see. I'm looking at you guys, not the screen. Velocity equals frequency times wavelength. So wavelength equals velocity over the frequency. So I can say Ln equals n times n over 2 times the velocity over the frequency. Right? Well, what if I want to know the different frequencies? F sub n, the different frequencies that will resonate in that pipe, is going to be equal to, what if I hold the length fixed? That's going to be n over 2 times the speed of sound over L. Okay? And so this will give me the different frequencies that will resonate in a given length of pipe. If you know the speed of sound, you know the length of the pipe, these are the different frequencies that will resonate. Lastly, I can make those frequencies resonate in this pipe. I'll have multiple frequencies resonating. Here's what I'm going to do. I'm going to go, when my wife walks by. Okay? Now I'm going to whistle like that into the pipe. Do you hear that certain frequencies were getting amplified? It sounded like it's going up and down in pitch. Here's a better pipe. This one's a little longer, so it's better. So different frequencies are resonating in that length of pipe, and this is the equation that gives it to you. Okay, that's it.